Bismillah ar-Rahman ar-Rahim. Hi everyone, my name is Abdussalam Khamis. I am the co-author of this scholar work that I am about to represent, which entitles Computer Simulation of a Series Connected Induction Generator and Determination of Minimum Required Capacitance for Self-Excitation for Wind Energy Application. This scholar work is done by Abdussalam Khamis from the Department of Electrical Engineering, College of Engineering Technology in Libya, and Dr. Saeed Ahmed Zaid, Department of Electric and Computer Engineering, Boise State University, USA. In this presentation, we'll talk about the abstract and then introduction, and then we'll talk about the mathematical model of a wound-rotor induction machine and the series connected induction machine. We also will introduce self-excitation for series connected induction generators and the minimum capacitance for self-excitation, steady state performance of a self-excited series connected induction generator, and we will end up with the conclusion. The abstract: when the stator and rotor windings of a conventional three-phase wound-rotor induction machine are connected in series but with opposite phase sequence, a series connected induction generator is created. For these machines to become self-excited, the machine terminals must be connected in parallel with the three-phase capacitor bank. In this paper, Direct-Quadrant theory and space vectors are applied to investigate the performance of a series connected induction machine operating as a standalone generator. For example, a wind turbine applications. Accurate and complete models of the generator at no load and with the resistive and resistive-inductive loads are derived. The minimum capacitance for self-excitation at constant speed is also obtained at no load and as well as when the generator is loaded. Numerical simulation predict the generator output voltage and the power output during the steady state operation. The paper motivation: reduce the dependency on fossil fuels as the only source of energy. Evaluate the potential implementation of series connected induction generator for standalone wind energy systems. Supply isolated communities. We hope for the contribution, derive an accurate computer model of series connected induction generators, calculate the minimum capacity required for self-excitation, and finally predict the steady state behavior of self-excited series connected induction generator. The mathematical model of wound-rotor induction generator and the series connected induction generator. At first, we made some assumptions to make our model of the generator much easier and applicable for computer programming. General assumption for the modulation: the machines under investigation is symmetrical, which means number of turns in the stator winds equals to number of turns in the rotor side. The stator and rotor winds are identical and distributed in the sinusoidal configuration, and also assume that the machine air gap is uniform. And then we made a model for a wound-rotor induction machine. We start with flux linkage equation, as we can see from the matrix. The column matrix, which represent lambda SA and lambda SB, etc., which represent the flux linkage for the stator windings. We'll start with S and the rotor windings with R. L1, L2, which represent the inductance and the self-inductance of the machine. And the last column matrix represent the currents in the stator and rotor windings in three-phase form. So, in order to summarize the effect of the flux linkage and the current on the machine performance, we use the space vector form. The space vector form gives us the effect of the flux in the and the currents in the stator wind and the rotor winds, as we can see from this slide. Therefore, the state flux linkage equations can be expressed concisely as written in equation 6 and 7, where Ls equals to LLS plus 2/3 LMS. Lm, what represents the mutual inductance, equals to 2/3 MSR, what represent the mutual inductance between the stator and rotor windings, and the same thing for the rotor windings for sure. Finally, we after mathematical manipulation of the equation 6 to 6 and 7, we got the voltage equation for space vector. Well, the Vs equals to RSIS plus d lambda s over dt, and Vr equals to RRIR plus dir over dt. And we end up with the two equations which represent the torque, the devolved torque by the induction machine, and the rotor speed as written in equations 10 and 11. So now we move on from the compact three-phase representation of voltage and torque equation into the dq representation of the voltage and the torque. The t represent in a direct axis, and the q in the quadrature axis. This straightforward equation are very simple to model in a computer environment as we use in the MATLAB, as we can see from equation 12 to 16. Now we will talk a little bit about the series connected induction generators. The model of a series connected induction generator. A series connected induction generator is simply a wound-rotor three-phase induction machine recognized with it is a stator and rotor windings connected in a series. The stator and rotor connection should be with the opposite phase sequence, as we can see from the figure B, where the figure A represents the conventional wound-rotor induction machine, and figure B represents the series connected induction machine. So when the stator and rotor windings are connected, we got the current will be the same. So the I represent the current flows in the rotor and stator winding, equals to Is equals to IR conjugate, and the conjugate, by the way, it represents the opposite phase sequence. Lambda equals to lambda S plus lambda R equals to LA plus MEIJIR conjugate. Now we have the voltage equation as in 19 and 22 represent the torque equation of the series connected induction machine. And the same thing that we have made with the wound-rotor induction machine, we may get with the series connected induction machine. So we represent it in dq form. So we have a Vd equals to I RID plus LD dit over dt minus omega over 2 LQ IQ, and Vq equals to RIQ plus LQ diq over dt plus omega over 2 LDID, and the same thing we get the torque equation called P over 2, where P equals number of poles, 2/3 to Lm IQ ID. Now we will talk about the self-excited series connected induction generator. The theory of self-excitation. Self-excitation is a phenomenon that allows voltage to build up in the terminal of induction machine. Condition for self-excitation: the rotor should have sufficient residential magnetism. The capacitor bank should have sufficient value. After mathematical manipulation, we got this matrix which represent the series connected induction generator with the capacitor bank when at no load, where C represents the capacitor connected to a terminal of the stator windings. The same thing, we created a matrix which represent the complete model of series connected induction generator when it is loaded by purely resistive load. And this matrix represents the complete model of series connected induction generator at resistive inductive load was considered as a normal load, because majority of electric load are actually resistive inductive load. So now we move on for sure for minimum capacitor for self-excitation. This table provide parameters for the experimental generator that we used in our experiment. So the saturation representation of the experimental generator, in order for a series connected induction generator to become self-excited, it has to operate within its saturation region, as we know. So we draw the saturation curve, which represents a relationship between mutual inductance generator and stator, and the IM, which represents the magnetization current. And these just represent the actual saturation curve for the machine. But since we are building a computer model, we have to find out some sort of mathematical equation that we can insert in the program, MATLAB program, to represent the magnetization. So we make what's called the curve fitting for self-excitation. We got IMS, the magnetization, equals to 0.0048 IM in the power 4 minus 0.0438 IM square plus 0.2491. And this, as we can see from this figure, the mutual inductance and magnetization relationship that we will use for our model. And here is the minimum capacitor for no load, required for no load and for resistive load and for resistive and inductive load. Steady state performance of self-excited induction machine. At no load, we can see the line represent the simulation data and the dots represent the actual data. We can see the very close matching between the measured and data. The same thing for resistive load and the resistive inductive load. Conclusion: DQ theory provide an accurate model of a series connected induction generator at no load, purely resistive load, and resistive inductive load. The minimum capacitor required for self-excitation for both the extents of no load and 1200 watt resistive load are similar to one another. For resistive inductive load at 1200 watts and 3.2 Henry, the minimum capacitor required for self-excitation is this slightly higher than, for instance, for no load and purely resistive load.